Hey calculus class! Today we are going to talk about topic 68, Taylor and Maclaurin series. And this is actually our last topic for the BC class. So after this you should be able to do anything on the AP Calculus BC test. Alright, so we're going to start off by talking about Taylor and Maclaurin series. And basically if you want no error in your approximation, then you want the exact value of the function. In order to do this, you want the infinite degree of the Taylor polynomial. So a Taylor series is represented as the sum, as n equals 0 to infinity, of f to the whatever nth derivative of c over n factorial times x minus c to the nth power. And then we have the Maclaurin series, which is just the Taylor series centered at 0. These series now allow us to rewrite complicated functions as polynomials of infinite degree. But of course, this only works for x values where the series converge. So let's look at some examples. We want to find the Maclaurin series for y equals e to the x, and we also need to know for what x values does this series converge. So to do that, I'm going to take so many derivatives, and I just went up to the fourth derivative, and I'm going to evaluate each derivative at x equals 4, which in this case is all 1. And you only need to go as far as you need in order to see a pattern in the series. So that means I'm going to set up the terms for the Maclaurin polynomial for e to the x until I see a pattern so I can write a series. So the first term will be 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on. And I'm only going until I see a pattern, and up to this point I do see one, and if I was to rewrite this as a series, I would get x to the n over n factorial, where n equals 0. So now, in order for me to determine for what x values does this series converge, I need to find the interval of convergence. So that means I'm going to set up my limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, which is just the ratio test. And using exponent properties and factorial properties, I can expand out the factorial and the exponents so that stuff cancels. And I am left with the limit as the limit as n approaches infinity of the absolute value of x over n plus 1. I can pull out the absolute value of x. When I take the limit of 1 over n plus 1 factorial, I'm just going to get 0. And 0 times anything is going to give me 0. And so 0 is less than 1. So since 0 is always less than 1, this power series will converge for any x value. So that means my interval of convergence is all real numbers. All right, so for example 2, we want to find the Maclaurin series for y equals sine x, and for what x values does it converge. So I have y equals sine x, and I'm going to have to find so many derivatives until I think I'm going to be able to see a pattern. And I found the first derivative, second derivative, third derivative, and fourth derivative, and the fifth derivative. So I'm going to go ahead and evaluate each derivative at x equals 0. So when I do that, I'm going to get 0, 1, 0, negative 1, 0, and 1. And I'm going to cross off the 0 terms because when I multiply by 0, that term in the polynomial will cancel out. So I'm not even going to worry about writing those terms. So that means when I set up my sine x, I only have the odd index terms, which will contribute to the series. Right, so I have the first derivative term, the third derivative, and the fifth derivative, which means I'll have the seventh derivative, and so on. And so the first term of sine x will be x plus a negative x cubed over 3 factorial plus x to the fifth over 5 factorial. And if I wanted to keep going, I would then get a negative x to the seventh over 7 factorial, and so on. And when we write our series, you'll notice that we have an alternating series. So that means that in our series for sine x, I'm going to need to have a multiple of -1. So here's my multiple of -1 to the nth power, because I'm starting at 0. And since the first term is positive, that means that this -1 to the first term, whatever it is in this case the 0 term, has to be a positive 1. And then since I'm only dealing with the odd indexes, so the first term, the first derivative, the third derivative, the fifth derivative, and so on, that means in order to get odd exponents, I'm going to have 2n plus 1 all over the 2n plus 1 factorial. Now I'm going to go ahead and set up my ratio test to find the interval of convergence, and also use exponent properties to expand out so I can cancel stuff. And I can even expand out the 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, so that those will cancel. After canceling, I am left with x squared over 2n plus 3 times 2n plus 2. I can pull out the absolute value of x squared, and I went ahead and distributed through the bottom. So when I plug in infinity, I'm going to get 0 times absolute value of x squared, which is 0. And 0 is always less than 1, so this power series will converge for any x value. So the interval of convergence is all real numbers. All right, now let's do the Maclaurin series for y equals cosine x. So I'm going to go ahead and set up the derivatives, so many derivatives. So I got first derivative, second derivative, third derivative, fourth derivative, fifth derivative. Go ahead and evaluate at x equals 0. So I get 1, 0, -1, 0, 1, and 0. And I'm going to go ahead, the 0 terms don't matter. And if we notice this time with cosine, we have only the even index terms that will contribute to the series. So when I set up my polynomial for cosine, the first term will be 1 minus the x squared over 2 factorial plus x to the fourth over 4 factorial. And I could keep going, negative x to the 6th over 6 factorial, and so on. And you'll notice that this is also an alternating series. So I have to have a multiple of -1. And since I only want even terms, that means my exponent's going to have to be 2 times n all over 2n factorial. So to find my interval of convergence, I set up the ratio test, expand out, and I can also expand out using factorial properties of 2n plus 2 factorial to get the following. So now when I cancel, I am left with the absolute value of x squared over 2n plus 2 times 2n plus 1. All right, so I can go ahead and pull out the x squared and multiply through the denominator to get the following. And when I evaluate the limit, I'm going to get 0 times the x squared, which will give me just 0. And since 0 is always less than 1, this power series will also converge for any x value. So that means my interval of convergence is also all real numbers. So now let's try a Taylor series rather than a Maclaurin series. And in this example, we're going to do ln x, and we are given that it's going to be centered at x equals 1. And we also need to determine the x values that this series converges for. So I have y equals ln x. Find so many derivatives. First derivative, second derivative, third derivative, fourth derivative, fifth derivative. And I'm going to evaluate at x equals 1, since that's what I'm centered at. And so when I evaluate, we get 0, 1, -1, 2, -6, and 24. And I'm going to go ahead and set up the polynomial. So my first term is 0, which really doesn't do a whole lot. And then my next term is x minus 1 minus 1/2 x minus 1 squared plus 2 over 3 factorial times x minus 1 cubed. And I go ahead and keep going until I get enough for me to see a pattern. And so it will help to see the pattern if you were to simplify these out, so expanding out the factorials. And when you simplify the fractions, we see an more recognizable pattern. And so my series is going to be, it's an alternating series, so I have to have a multiple of -1. And if I start with n equals 0, I need this to be a positive. So that's why I have n plus 1. And then I got x minus 1 to the nth power all over n. I'm going to go ahead and set up my ratio test to test for the interval of convergence. Use exponent properties to expand out. I can cancel some stuff, and I can cancel some more stuff. So I am now left with n times x minus 1 all over n plus 1. I can pull out the absolute value of x minus 1. When I take the limit of this, I'm going to have to use L'Hopital, so I'm just going to get 1. So I'm left with the absolute value of x minus 1. And I need this to be less than 1. So that means I'm centered at 1. And if I need the radius to be less than 1, then, or the radius is 1, so that means I'm going to go between 0 and 2. I need to test my endpoints at 0 and 2 for the series to see if it converges or diverges. So when x equals 0, I'm going to get -1 over n, which diverges because negative multiples of the harmonic series. So that means I got a parenthesis at 0. And then I have x over 2. And when I do that, I'm going to get the following. And this converges because it's the alternating harmonic series. So I have a bracket at 2. So that means my interval of convergence for this series is from 0 to 2, including 2. All right, so we just found some of the special Maclaurin series for certain given functions. So we did find the Maclaurin series for e to the x, which was the following, and then the interval of convergence was all real numbers. We also found it for sine x, and that interval of convergence was also all real numbers. Then we also found it for cosine x, which was the interval, and the interval of convergence was also all real numbers. And we didn't do it for arctangent, but we can. And if you do, you would get the following series for arctangent. And that interval of convergence is -1 to 1, including the endpoints. And we, if we found the Maclaurin series of ln of 1 plus x, it would be the following, with an interval of convergence from -1 to 1, including 1. We can also do it for 1 over 1 minus x, which is just this following series, with an interval of convergence from -1 to 1. And we can also do it for 1 over 1 plus x, which gives me -1 to 1. So we are also going to be finding series for versions of known series. So by knowing the common 7 series, the ones that I just listed, we can rewrite variations of the functions as a similar series. And to do this, you're going to do something similar to U substitution. So that means if I was to have f of whatever, then wherever there's the x in my Taylor series, I'm going to replace that with the u, or the inner function. So for example, if we have y equals e to the 2x, well, that's pretty familiar to e to the x. So instead of using e to the x, I'm going to use e to the u. And so this would be my e to the u series, and instead of in terms of x, it's in terms of u. And since I'm letting u equal 2x, that means I'm going to replace u with 2x. So this, you can either say that this is your series, or if you wanted to expand out with the exponents properties, you would get the following series. And we can do the same thing for y equals cosine x squared. That's similar to just cosine of whatever, so cosine of u, and this is our cosine series. And I'm just going to replace u with x squared. And I can use exponent properties to simplify. Now, if you have one where you have, like this one, x squared times sine x squared, you're first just going to deal with the sine x squared, because whatever this series is, this x squared is just going to multiply it. So sine x squared is similar to sine u. Replace u with x squared, and then since the sine is being multiplied by x squared, the series also gets multiplied by x squared. And I can use exponent properties to simplify. And I can even pull in the x squared, so it will combine with this x to the 4n plus 2 to give me the following. Now we can also do calculus with Taylor series. So one reason that Taylor series are important is that they allow us to integrate functions that we couldn't previously integrate with other techniques. So for example, if we were to have e to the negative x squared, well, we can't do u substitution, and we also cannot do integration by parts. So how would we integrate this besides, using a good old graphing calculator with the CAS feature? Well, we're going to translate e to the negative x squared into a Taylor series. So e to the negative x squared is similar to e to the u, and then wherever there's a u, I'm going to replace that with negative x squared. And I can use exponent properties to simplify. Now that the function is rewritten as a polynomial, we can now integrate it. So that means if I was to expand out this series, I would get the following: 1 minus x squared over 1 factorial plus x to the 4th over 2 factorial, and so on. Now, this is much more doable with integration, because I'm just going to use my good old power rule, add 1 to the exponent, divide by the new exponent. So when I integrate this, if I was to integrate each term, I would of course have my plus c, plus x minus x cubed over 3 times 1 factorial. I added the exponent, add 1 to the exponent, divide by the new exponent. Same thing with the next term, and then the next term. And then when I get down to the general nth term, I added 1 to the new to the exponent of x, divided by the new exponent. So this series will also converge for all of x, because the original series of the function converges for all of x as well. All right, now let's finally do some example AP questions that we have been waiting for. So this question is the number 3 off of the 2008 BC exam. So let h be a function having derivatives of all orders for x greater than 0. Selected values of h and its first four derivatives are indicated in the table above. The function h and these four derivatives are increasing on the interval between 1 and 3. So for part A, they want you to write the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. Is this approximation greater than or less than h of 1.9? And explain your reasoning. So for part A, when you're writing a first degree Taylor polynomial, that's the same idea as linear approximation. And we're specifically centered at x equals 2. So we're concerned with x equals 2. So that means my first degree Taylor polynomial is going to be 80 plus the first derivative times the factor to the first power, x minus 2. Now I'm going to go ahead and evaluate that at 1.9, which I will get 67.2. So now we have to determine if this 67.2 is greater than or less than the actual value on h at 1.9. Well, 1.9 is going to be pretty dang close to x equals 2, which we know on the actual function of h is 80. And since h is increasing on this interval, then we can say that the approximation on the Taylor polynomial is less than the actual value on the function h at 1.9 because h prime is increasing on the interval from 1 to 3. So for part B, we're going to write the third degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9. So this time I'm going to use all the way up to the third derivative. So doing that, I get the following Taylor polynomial. I'm going to evaluate that at 1.9, and I will get 67.9884. Now, for part C, we're going to use the Lagrange error bound to show that the third degree Taylor polynomial for h about x equals 2 approximates h of 1.9 with error less than 3 times 10 to the negative 4. So to set up the Lagrange error bound, that means that the h of 1.9 minus the Taylor polynomial of the third degree at 1.9, that absolute value, has to be less than or equal to the next term, which would be the fourth term of a. And the interval that you will use to help you determine the a value will be one close to the approximation. So in this case, it's going to be 1.9 to 2. So to figure out the a, I need to know that since the fourth derivative is increasing, the max will occur at x equals 2. So that means I'm going to use 2 for my a. And that means I need my fourth derivative at 2 over 9 times 24. I just took out the 4 factorial so I can simplify it more easily. And then after simplifying, I get 2.7 times 10 to the negative 4. And 2.7 times 10 to the negative 4 is less than 3 times 10 to the negative 4. All right, now let's try this example, which was from 2011, and it was question number 6, which means no calculator. So we have that we're going to let f of x equals sine of x squared plus cosine x, and the graph of y equals the absolute value of the fifth derivative is shown. For part A, we want to write the first 4 non-zero terms of the Taylor series for sine x about x equals 0, and write the first 4 non-zero terms of the Taylor series for sine x squared about x equals 4. So we know that the Taylor series for sine x around x equals 0 is going to be represented by this series. And so I need to write the first 4 non-zero terms. So I'm just going to go ahead and put 0 in for the n and all the way up to 4. So I get these would be my first 4 terms. Now I'm going to do the same thing with sine x squared, which, using the u substitution idea, I get the following series. And then just expand out for the next 4 terms, I get x squared minus x to the 6th over 3 factorial, and so on. For part B, we are going to write the first 4 non-zero terms of the Taylor series for cosine x about x equals 0. And then we're going to use this series and the series for sine x squared found in part A to write the first 4 non-zero terms of the Taylor series of f about x equals 0. So this function. So cosine x we know is represented by the following series. So when I expand it out, I get the first 4 terms. And now I'm going to go ahead and use these 4 terms and these 4 terms. And according to the function of f, I'm going to add them together to get the first 4 non-zero terms of the Taylor series. So since I have sine x squared first, I'm going to go ahead and put those 4 terms for sine x squared in first, plus the 4 terms for cosine x, and I get the following. And then I can go ahead and combine like terms, and I'm only focused on the first 4 terms. So after I combine the 1 and then the x squared term, x fourth term, and x sixth term, I already have my 4 terms, so I don't need to worry about the x to the 10th or the x to the 14th. Now for part C, we want to find the value of the 6th derivative at 0. All right, so this means that I want the coefficient from the x to the 6th Taylor series of what I just wrote about x equals 0. And that I found in the previous one, and the coefficient on the 6th derivative, or the x to the 6th term, was negative 121. Now for part D, we're going to let p of 4 of x be the 4th degree Taylor polynomial for f about x equals 0, using information from the graph of the absolute value of the 5th derivative, show that the absolute value of the p of 4 of 1/4 minus f of 1/4 is less than 1 over 3,000. All right, so we need to refer back to the graph from the beginning. And from the graph, if we look just at the interval from 0, because I'm centered at 0, to 1/4, because that's where I'm looking at my error to be. So from 0 to 1/4, which would be right here. So I'm looking at just this part of the graph. That the maximum of the 5th derivative has to be less than 40, since this is the graph of the 5th derivative. So therefore, I can say that the error has to be less than or equal to 40 over 5 factorial times x to the 5th. And since I'm looking at between 0 and 1 to the 4th, you can see that the maximum is going to occur at the 1/4, since this is increasing. And then if I evaluate that and keep evaluating, I would get the following. And this is less than 1 over 3,000. So I had just shown that the error is less than 1 over 3,000. Well, I hope you enjoyed learning about Taylor and Maclaurin series, and I will see you in class tomorrow. Have a good night.